Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the synthesis of Longifolene. In a previous lecture, we have discussed about the Longifolene. There we know that the structure of Longifolene, what are the characteristics of that Longifolene, and if you remember the Longifolene, if you observe the structure of Longifolene carefully, you would observe there it is a tricyclic, it is a hydrocarbon, there are 4 chiral centers, and it is a natural product, and as we know that natural products are obtained from the various parts of the plants. And why there is a need to study such type of the natural product? Because most of the natural products are optically active in nature and they exhibit the prominent or the significant physiological action or the medicinal point of view. It is they are useful as a medicine, and therefore there is a need to study such type of the compound. If you observe this structure carefully, the aim or the objective behind to study this Longifolene is mainly the student should acquire the adequate method for making as a carbon-carbon new bond or new carbon-carbon bond, and therefore by knowing the various known method how we can able or student can able to form the new carbon-carbon bond, that is the main objective behind to study this type of the natural products. And in a previous lecture we have discussed the first way of synthesizing that Longifolene by using different suitable solvent and keeping as a reaction condition, proper reaction condition, maintaining as a stereochemistry, and that type of the discussion we had discussed in our previous lecture. So as we know that there are the 9 different ways to synthesize that Longifolene, starting from the various different starting materials via different routes involving some of the named reactions. And we know that these Longifolene, for in the first lecture we have done retrosynthetic analysis of that Longifolene, and we have reached to the starting material which is readily available or easily available, and from that we can synthesize that Longifolene, which is a natural product, natural organic compound, but extracting such kind of the natural product from the various parts of the plants, and we know that plants are limited one, but if you synthesize the same compound in the laboratory, we can make this compound in a large scale, which is useful for mankind, or whatever properties that exhibit, it will be helpful to the society, and that's why we are trying to. But while doing as a retrosynthetic analysis, we are breaking as a bond and making as a bond. There are the different terms involved in the retrosynthetic analysis. Retrosynthetic analysis means the process of breaking down target molecule into convenient starting material using disconnection and functional group interconversion is known as a retrosynthetic analysis. But whenever we have got as a starting material which is a Wieland-Michler ketone, which is a starting material, is found suitable here for the synthesis of that Longifolene. There are 9 different ways. So let us start to synthesize. The second way of synthesizing this Longifolene, that is a scheme number 13.24. I am describing here, I am explaining here. Try to see here. Let's say the Wieland-Michler ketone, which is a starting material, which we are going to consider here, this one. If you observe the structure carefully, what do you see over here? Here the A reagent I am adding here. Let's see first one in bracket, here HO, then CH2 twice, that is a diol, 1,2-diol. Second one which we are adding here, that is a H2 in presence of palladium charcoal. And the third reagent which we are adding here is this one. Everybody knows that CS3 Mgi. And the fourth one which I am adding here as a H plus. These are the reagent adding step by step. Finally, what type of the product do you get here? Can you predict the product? If you see these reagent one by one, you can clearly know the individual uses of each reagent. These are the organic reagent, and we are studying this organic reaction. If you observe this starting material which is readily available, or we can call it as a easily available, which is known as Wieland-Michler ketone. Look at here, there are 2 carbonyl group present in this organic compound. One is the individual carbonyl group and another one is alpha beta unsaturated carbonyl group. Now tell me, among these 2 carbonyl group, which one is a more reactive one? Whether the isolated carbonyl group is a more reactive or conjugated carbonyl group is a more reactive? What do you think? You can easily recognize, or you must remember here, individual carbonyl group, or what we can call it as here, isolated carbonyl group is a more reactive toward the nucleophilic substitution reaction, because here the carbonyl carbon is a electrophilic in nature, more electrophilic, so that, or we can call it, it is a reaction center where the nucleophile can attack more easily as compared to as this one, because this is alpha beta unsaturated compound. When it becomes as alpha beta unsaturated compound, then the nucleophile has 2 options where to attack. It can attach at beta position, or it can attach at directly carbonyl carbon atom. Therefore, the reactivity of this what we can call it as a alpha beta unsaturated compound, due to the resonance effect, it is less reactive toward the nucleophilic substitution reaction as compared to as a isolated carbonyl group. This is alpha beta unsaturated compound. If you add one by one reagent or the step by step, you will get here this reagent we can write CH2, then this CH2, and then OH. This is a 1,2-diol which is known for the protection of the carbonyl group. And which carbonyl group is going to protect, which is more reactive? Look at here, this will get reacted easily, it get protected, and as we know that protection is carried out when there is we require the desired product. If you keep as it is, we won't get the desired product without the protection of, and therefore protection is or what we can call it as the installation of the group in a particular organic compound to get the desired product, or to mask the most reactive functional group. First, to decrease the reactivity of that reaction center toward the particular, and then you can add the proper reagent so that you can convert one of the functional group into the desired product. So that's why we are doing the protection to get the desired product. Now here this is going to protect over here an alpha beta unsaturated compound, alpha beta unsaturated carbonyl compound remains as it is. So that is what we can call it as a use of this reagent to protect the carbonyl group selectively. Now in the second reagent which you are adding here, H2 in presence of palladium charcoal, it is also has a speciality. Can you tell me whether it is a oxidizing reagent or reducing reagent? It is a reducing reagent, and there are there are different type of the reducing reagent, and each reducing reagent has their own speciality. If you remember here, it can reduce this H2 in presence of the what we can call it as a palladium. It selectively reduces, it selectively convert carbon-carbon double bond into as a single bond, or maybe as a carbon-carbon triple bond into as a single bond. Means unsaturated compound becomes as a saturated. Other carbonyl group or that do not get reduced by this reagent. So that is the speciality of this H2 in presence of palladium. For example, suppose you have this type of the compound, carbon-carbon double bond. This is a alpha beta unsaturated compound. H2 and palladium, if you use, you will get the compound is a cyclohexanone. Alpha beta unsaturated compound we can get into as a cyclohexanone. That is the speciality of this. Suppose you have this type of the compound over here, there, suppose as a C triple bond, and then you use as a H2 in presence of palladium charcoal, the resulting compound will be obtained is this one, then CH2 NH2. Benzyl amine you are going to get. Suppose you have a amine there, here CH double bond, N maybe as a CH3, that type of the imines are there. If you treat with H2 in presence of palladium and charcoal, imine also get converted into as this type of the compound, CH2, then NH, then CH3, this type of the compound you will get over there. So that are the speciality of this. So you might now able to understood this one. So what you are going to get? You are going to get the product over here. This is a protected group, remains as it is. This is the methyl group, now is a carbonyl group, and this group get reduced over there. So that is a speciality. And now as we know that, then you are using the Grignard's reagent CS3 MgBr, methyl magnesium bromide. What it will do? It will convert that ketone into as a tertiary alcohol, and then you are going to get the product over here. So this type of the product, not this one. Let me draw properly here. So here you are going to get OH. Here is a methyl group. Then this is a methyl group, and here maybe as a hydro. The stereochemistry here is a cis over here, and here you are going to get as a this type of the compound. And when it is further treated with H plus, what is going to get? The hydrogen, loss of water molecule, and this get deprotected, and finally you are going to get the product which I am writing here. This carbonyl group get deprotected whenever we require. Here as a methyl group, here also as a methyl group, and the double bond comes at this position. So this is the product which we got over here. Here is a hydrogen atom. By adding all these reagents, finally we would end up with this product. This is the product which we got over here. Now let me clean this over here. And once you got as a, by adding as a these A reagent, we got this one, and now we are going to add, here is a B reagent. What are those B reagents? So let's see over here. First one is a ArCO3H, and second one will be this one, as you might be knowing, CS3 S double bond O CS3. This is known as a DMSO, dimethyl sulfoxide, used as an solvent, and this we know that this is a per acid. Per acid, which per acid? That is a perbenzoic acid. Here indicate as a substituted mainly as a metachloroperbenzoic acid. So that type of the reagent may be there. This is a B, and after adding these reagent, B reagent, what finally you are going to get? And by adding these reagent, this will form as a epoxide over here. Remember, here there is a carbon-carbon double bond. Epoxide is going to form over there, and then there is a sulfoxide, then it can form as a ring over there, and finally the product which you are going to get over here, which I am writing here. So you can remember, this is the product which we are going to get. One methyl group over here, there is a hydrogen atom that is showing as a stereochemistry over here, and here is a methyl group, here is a carbonyl group. So this is the product we would get over here by adding these reagents suitably. So we can show here stereochemistry. Let me show properly here CS3 and one hydroxy group over there. And now when these reagents, not reagent, this is a compound which we got from this. By adding these reagents suitably, we got this tricyclic ring, and now this compound further treated with the C reagent. What are those C reagent? Let's see. First one is a H plus. What it will do? It will remove the water molecule from the starting material, and second one is this one CHBr3, that is a CHCl3, we are calling it as a chloroform. Similarly, it is a bromoform. So bromoform, and then it will be treated with third one KOC, then CH3 thrice time. that is a tertiary butoxide, potassium tertiary butoxide. These are the reagent. When you are adding over here, what the product you are going to get here, remember H plus, it will form as a double bond. This side there is no hydrogen atom is there, but possibility to form as a double bond. This side preferentially due to the what we can call it as a here, let me recall over here, this is a bicyclo type of the compounds over there, and that hydrogen atom is very difficult to remove. Preferentially the hydrogen which is lost from here, double bond are easily formed over there, and there is a removal of water molecule. Then chloroform, it will provide the, or we can call it, it's a source of bromide over here. And finally the product which we are going to get over here, let me draw that structure once again over here. So this is the structure which we are going to get over here. Here Br, here also as a Br, and one methyl group which I am writing as it is, this methyl group as it is, and this carbonyl group are as it is. Only changes are occur at this part only. One which is formed as a double bond, bromoform, there is a what we can call it as a formation of that type of the compound over there. This is a tricyclopropane type of the derivative we are going to get here. And now when these reagent, this is a C reagent, when we are adding C reagent, we are getting as a this type of the compound. Now after that we are adding as a D reagent. What are those D reagent? Let us see one here. Here is a Ag plus, that is a silver is added over there, and second one, or we can call it as a argentite here, and second one will be the Cr, that is a 6, that is a chromium 6, which is a strong oxidizing reagent. What it will do, it will oxidize this group over there, hydroxy group Ag plus, it will remove that Ag plus. That Ag plus, as we know that it is a very it has a great affinity toward as a halide. It combined with that halide, remove that halide and form as a this double bond is formed over there, and here you are going to get as a product is like this. There is a some rearrangement type of the some carbon skeleton rearrangement properly is orange over there, and finally you are going to get the product which is like this. So you can easily see this product, double bond over here Br, and one of the methyl group which is here, and carbonyl group which is over here, not here, here must be as a methyl group, not the Br, and here at this position which is remains as a methyl group. Other part of this compound remains as it is. So finally now this compound when treated with the reagent like D reagent, what are those D reagent? Let us see here. First one is a sodium metal which is added over there, sodium bromide can form, and then after that it will be treated with methanol in presence of ammonium NH3, and second one oxidizing reagent which is a chromium 6, that is again the strong oxidizing reagent which can oxidize the particular group, so that we are going to get the product over here suitably. What you are going to get the product which I am going to represent over here. Let's see here, this compound remains as it is. Now we can draw this compound here as it is. Here is a methyl group as it is over there, and then here is a double bond and carbonyl group is comes over there. This carbonyl group, it is as it is, and the methyl group which is also as it is over there. Only we brought here, we remove the Br from this by adding this type of the reagent. This is called as a D reagent. Now this structure, this organic compound further treated with the reagent, maybe as a F reagent. Here is a F reagent. When F reagents are adding, what are those F reagents? Let us see here, which is first one CS3 twice CuLi, which is a Gilman's reagent. And as we know that Gilman's reagent, this is alpha and this is a beta. Now Gilman's reagent known for 1,4 addition reaction. 1,4 addition reaction can be carried out over here, and you are going to get methyl group is going to insert at this position, and we will get the product is this one. Let's see, the product is this one. This is a product. Here are the methyl group. Now the carbonyl group which is at this position remains there, and now this is the compound which we got over here after adding as a F reagent. So here carbonyl group remains as it is, and this methyl group also as it is. These are the methyl group which is showing here clearly is this one. And now let me clean this part of the board so that you can see this properly over here. So now this is the compound which we got after adding as a F reagent. Now we are going to add, here is a G reagent. G reagent, what are those reagents? Let's see one by one. One is a sodium borohydride, NaBH4, and as we know that sodium borohydride, it is a reducing reagent. And second, we are adding as a methyl lithium. Methyl lithium also as a one of the strong base used over there. And then third one which is adding here CS3 SO2Cl, that is methyl sulfonyl chloride. And in fourth one again adding as a KOC, then CS3 thrice, that is a tertiary butoxide added over there. And fifth one, as we know that here is a H2 in presence of what we can call it as a RH, then PPH3, then Cl, PPH3Cl, that as we know that it is a Wilkinson reduction. Wilkinson reduction, this reagent is known as a Wilkinson reagent. Wilkinson reagent is, or Wilkinson catalyst, we can call it as a catalyst. So it is also as a one of the reducing reagent which is selectively reduce the particular carbon-carbon double bond which we are going to get over here. Now, and after adding all these reagents, now look at here, carbonyl group over there, then this is also as a carbonyl group which is going to reduce out of these two, one is going to reduce this one, so that is converted into as a carbohydrate. And finally, so the product which you are going to get, so that is this group get removed over there, and you are going to get the product like this. This is the compound which we are going to get over here, methyl group, carbon-carbon double bond, 3, 4. So this is a compound which we are going to get over there. Now here, so, and finally if you add here the Wittig reagent, we know that PS3 P double bond CH2 Wittig reagent, and what you are going to get? You are going to get as a Longifolene. So in this way we have get the Longifolene by using as a second method. I think with this let us stop. I think we have seen these type of the compound. Second one, second way of synthesizing as a Longifolene, how we got this target molecule, and as we know that the structure of that Longifolene Wittig reagent only, this is the compound which we are going to get over here, this one. Here the compound which we are going to get is this Longifolene structure, as we know that. So let's see this. We are going to get, here is a methyl group. Here remember this methyl group remains as it is. This carbonyl group is suitably converted into as a carbon-carbon double bond. Here are the methyl group, and this is nothing but our target molecule. So in this way we have seen this is a compound which we got. So I think remaining synthesis we will see in the next lecture. Let us stop today here. Thank you. Have a nice day.